Our universe might be just one room in an infinite cosmic mansion. We are about to explore 25 astonishing theories on how multiple universes could interact, moving far beyond simple parallel worlds into realms of colliding dimensions and quantum bridges. By the end, you will possess a new framework for understanding reality itself. What if the stars we see are echoes from a neighboring cosmos? Could a single particle be entangled with its twin in another reality? The answers challenge everything we think we know. What feels most real to you about the world around you? The first and perhaps most visceral theory of multiverse contact is that of cosmic bubble collisions. Picture a pot of water just beginning to boil. As the heat rises, tiny bubbles form, expand, and rise to the surface. Some may even merge as they grow. Now replace the water with an eternally inflating quantum field and each bubble with an entire universe. This is the landscape of eternal inflation, where new universes constantly pop into existence, each with its own potentially unique laws of physics. Our entire observable cosmos is just one of these bubbles, forever expanding within an incomprehensibly vast foam. The interaction happens when two of these expanding bubbles, drifting through the higher dimensional void, finally touch. The moment of contact would be a cataclysm of almost biblical proportions, a shock wave of pure energy propagating through the fabric of both universes. For us, the evidence would be written in the oldest light we can see, the cosmic microwave background. A collision would leave a distinct circular imprint, a kind of cosmic bruise, where the temperature and polarization of this ancient radiation are dramatically different. Cosmologists have been meticulously scanning the sky for these telltale scars. Finding one would be the first direct physical evidence that we are not alone in the grandest sense, that other cosmic realms are literally bumping into ours. But the implications go far beyond a simple mark. The energy released in such a collision could be so profound that it rewrites the local laws of physics at the boundary. It might seed the formation of bizarre new galaxies or even trigger a secondary, localized Big Bang event within our own universe, creating a pocket of space-time governed by entirely different rules. This theory transforms the multiverse from a philosophical idea into a dynamic, sometimes violent, architectural structure, where universes are born, grow, and occasionally crash into each other in the dark. These concentric rings in the cosmic microwave background would be the ultimate smoking gun. Teams analyzing data from the Planck satellite and other observatories are not just looking for random hot or cold spots. They are searching for specific, circular patterns of temperature variation that defy conventional cosmic inflation models. It is a needle in a haystack exercise on a universal scale, sifting through the faint afterglow of creation itself for a signature that says we are not alone. Finding even one such pattern would shatter the paradigm. It would move the multiverse from theoretical physics into the realm of observational science, providing the first tangible proof that our universe is part of a far vaster, interactive structure. The philosophical weight of that discovery is staggering. It would mean our entire cosmic history, from the first second of the Big Bang to the formation of our solar system, might have been influenced by an external force, a literal nudge from a neighboring reality. From inside our bubble, what would such an interaction actually look like? The terrifying and fascinating answer is, it might have already happened, and we just have not recognized it yet. If a collision occurred in the distant past, its evidence would be fossilized in that ancient light, a silent monument to a forgotten encounter. But if one were to happen now or in our future, the experience would depend entirely on scale and distance. A direct nearby impact could be unimaginably catastrophic, a wall of fundamental force rewriting physics as it approached, potentially unraveling space-time itself. Yet a more distant, glancing blow might manifest as a subtle but persistent anomaly, a region of space where gravity behaves oddly or where the speed of light seems slightly different. It could appear as a mysterious void in the galaxy maps or a source of inexplicable energy with no visible cause. This theory forces us to confront a humbling possibility. The laws we consider immutable and universal might only be local bylaws, stable only until our cosmic bubble brushes against another with a different set of rules. That faint cosmic bruise is a mark left by a force from outside. But what if some connections are woven into reality itself, operating silently beneath the surface of everything? The second theory takes us to the heart of quantum strangeness and proposes a connection far more intimate than a collision. It suggests that quantum entanglement, the phenomenon Einstein famously called spooky action at a distance, might not be confined to our universe at all. In our world, entanglement links two particles so profoundly that measuring the state of one instantly determines the state of the other, no matter how far apart they are. This link defies classical intuition, seeming to communicate faster than light. Now, extend that principle across the multiverse. In the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event actually happens, but in a newly branched separate universe. When you measure a particle here and find it spinning up, another version of you in a parallel branch measures the identical particle and finds it spinning down. The radical proposal is this: what we perceive as spooky action within our single universe might actually be the ghostly echo of entanglement between these two identical particles now residing in different but still connected branches of reality. They are not communicating faster than light. They are simply two parts of a single quantum entity that is now stretched across the multiverse. The implications are staggering. It means that every act of observation, every quantum choice, might not sever a connection but simply transfer it into a higher dimensional framework we cannot directly perceive. This cross-universe entanglement could manifest in our reality as those subtle, non-local correlations that seem to defy explanation, little knots of statistical weirdness in experimental data that hint at an influence from outside our causal sphere. How could we ever test such a thing? One thought experiment involves creating a complex entangled system here and then deliberately trying to trick it. If you could design an experiment that somehow measures the system in a way that would be logically impossible if it were only entangled within our universe, yet the data still shows a correlation, that anomaly could point to a partner particle in another branch influencing the result. It is a faint signal to look for in the noise of quantum experiments, a signature of a handshake from another version of reality. If proven, this would utterly redefine not just quantum mechanics, but our very concept of individuality. It would mean that at the most fundamental level, you are not entirely separate from the other versions of you making different choices in other worlds. There is a thread, however fragile and quantum, that still binds those branching paths together. This theory suggests we are not isolated islands of consciousness, but part of a vast, entangled network of selves, a cosmic web of possibility where every choice resonates across the multiverse. This fragile quantum thread suggests a connection woven into reality's fabric. But what if our entire universe is just a sheet in a cosmic book, and the page next to it is about to turn? The third theory emerges from the depths of string theory, a framework where the fundamental particles are not points but tiny, vibrating strings. In this view, our familiar 3 dimensions of space and 1 of time are not the whole story. Our universe might be a 3-dimensional membrane, or brane for short, floating within a higher dimensional space called the bulk, and we are not alone. Other branes, other entire universes with their own laws, could be drifting in this hidden expanse parallel to our own. The interaction here is not a gentle quantum link, but something far more dramatic, a collision. This is the heart of the ekpyrotic or cyclic model of the cosmos. It proposes that our Big Bang was not a singular creation from nothing, but the explosive aftermath of 2 of these colossal branes smashing together. Think of it like two sheets of rubber floating in a vast, dark room. They are drawn together by a force across the bulk, and when they meet, the impact releases an unimaginable torrent of energy. That energy, confined to our three-dimensional brain, becomes all the matter and radiation we see around us. It is not a beginning from a singularity, but a rebirth, a big bounce from a previous phase of existence. This collision would have been violent and chaotic, but also incredibly smooth and uniform on the largest scales, potentially solving a major puzzle in cosmology known as the horizon problem. This problem asks why the universe looks so similar in all directions, as if distant regions had once been in contact, even though there has not been enough time since a traditional Big Bang for light or information to travel between them. Cosmic inflation is the usual solution, proposing a period of ultra-fast expansion to smooth everything out, but the brane collision offers an elegant alternative. Because the two branes are parallel and flat, their contact happens everywhere at once, like two sheets of paper coming together. This simultaneous, everywhere impact naturally creates a universe that starts off uniform and flat without needing a separate inflationary epoch. The echoes of such a titanic event might still be ringing through the cosmos today, not in light but in gravity. The violent shudder of the collision would have sent powerful ripples through the very fabric of space-time, primordial gravitational waves with a distinct signature. Our most sensitive detectors, like future space-based observatories, are listening for this specific hum. Finding it would be like discovering the fingerprint of the brane that struck us, proof that our universe was born from a clash of giants in a hidden dimension. This theory reframes cosmic history as a cycle, not a linear story. Our expanding universe will eventually stretch thin and cold. The brane will drift apart, only to be drawn back for another cataclysmic embrace, resetting the cosmic clock in an eternal rhythm of collision, expansion, and renewal. The cosmic brane collision reshapes our entire history. Yet another theory suggests the interactions we have described might not be physical at all, but something far more fundamental, an exchange of pure information. This is the holographic principle, one of the most profound ideas in modern physics. It proposes a staggering possibility. All the information that describes everything within a three-dimensional volume of space, every star, every planet, every person, is actually encoded on a two-dimensional surface that surrounds it like a cosmic DVD. Our three-dimensional reality, with all its rich depth and solidity, could be a projection from this flat, informational boundary. Think of it like watching a movie. The vivid, three-dimensional world you experience on screen does not exist inside your television. It is projected from the flat, two-dimensional data on a Blu-ray disc. The holographic principle suggests our universe operates on a similar, though infinitely more complex, principle. Our cosmic horizon, the farthest point from which light has had time to reach us, might be that disk, that ultimate screen where the data of our existence is written. Now extend this mind-bending logic to the multiverse. If our universe is a holographic projection, then perhaps other universes are too, each with its own bounding surface. An interaction between two such universes would not need to be a collision of matter or energy in a higher dimensional bulk. Instead, it could be an exchange of information between their respective boundary screens. The physics happening inside one volume, the dance of particles and forces, could be translated into a complex code on its horizon, and that code could, in principle, interact with the code from another universe's horizon. This transforms the problem of multiverse contact from one of brute force physics into one of communication and data processing. The work of physicists like Juan Maldaisner provides a potential mathematical key to understanding this. His discovery, known as the anti-de Sitter/conformal field theory correspondence, or AD-SCFT, is a concrete realization of the holographic principle in a specific, though hypothetical, type of universe. It establishes a perfect dictionary between a theory of gravity operating in a bulk volume and a quantum field theory without gravity living on its boundary. In this framework, a phenomenon inside the universe, like a black hole swallowing a star, has a perfect, albeit incredibly complex, description as a thermal process on the lower dimensional boundary. While our universe is not exactly of the type described by Maldacner's model, the principle is revolutionary. It suggests that if we can ever properly describe our own cosmos as a hologram, then interactions with other universes might be understood as correlations or entanglements between the quantum data on their separate screens. Two universes could talk to each other not by exchanging particles, but by having their boundary information become linked. A fluctuation in the quantum code on our cosmic horizon could, in this view, be the decoded signal of an event in another reality. This idea pushes the limits of what we consider real. It implies that the solid world we touch and see is a magnificent illusion, a readout from a vast cosmic hard drive. And if that is true, then the most fundamental level of existence is not space and time, but information, bits and bytes of data on the ultimate screen. The search for multiverse interactions becomes a search for glitches in that data, for patterns in the cosmic code that cannot be explained by internal processes alone, signatures written in the language of reality itself. That cosmic code on the boundary screen defines our reality from within. But what if something outside is pulling on the strings? The fifth theory points to a strange and persistent anomaly in the motion of galaxies, a ghostly current in the vast ocean of space that seems to flow from a source we cannot see. Astronomers call it the dark flow. Imagine you are in a boat on a perfectly still lake. You drop an anchor and expect to drift randomly with subtle, local currents. But instead, you and every other boat on the entire lake begin drifting slowly but steadily in the exact same direction. That is the unsettling puzzle presented by the dark flow. Surveys of thousands of galaxy clusters, the largest gravitationally bound structures in the universe, reveal that they are all streaming together at incredible speeds, millions of miles per hour, toward a specific point in the cosmos, far beyond the edge of our observable horizon. This is not the general expansion of the universe which pulls galaxies apart. This is a directed, coherent motion, as if everything is being tugged by an immense, unseen hand. The standard model of cosmology has no place for this. Within our observable universe, matter is distributed roughly evenly on the largest scales, so there should be no single, overwhelming gravitational source in one direction to cause such a uniform flow. The gravitational pull from all the visible matter we can map cancels out. The only plausible explanation within our current understanding is that the source of this titanic pull lies outside our cosmic bubble. This is where the multiverse theory enters. That relentless tug could be the gravitational influence of a neighboring universe, or a colossal mass structure in the wider multiversal landscape, exerting its force across the dimensional divide. It would be like feeling the breeze from a door left open in another room of the cosmic mansion. The evidence comes from meticulous observations of the cosmic microwave background, the same ancient light we discussed earlier. As galaxy clusters move at high speeds through this radiation, they create a subtle distortion known as the kinematic Sunyaev-Zeldovich effect. It is an extremely faint signal, but by studying it across hundreds of clusters, scientists have charted this mysterious coherent motion. The controversy is intense. Some researchers argue the statistical signal is too weak or could be explained by systematic errors in the data. Others see it as one of the most significant anomalies in modern cosmology, a potential crack in the wall of our observable reality. If the dark flow is real, what would the external universe causing it look like? To exert such a pull across what might be an unimaginable void or a higher dimensional barrier, it would need to be staggeringly massive, perhaps a universe with a far denser concentration of matter than our own, or one that underwent a different kind of inflationary expansion, leaving behind gravitational imprints that still reach us. Alternatively, it might not be a whole universe but a single, monstrous structure within the multiverse, a cosmic supercluster on a scale we can barely comprehend. Mapping the precise direction and amplitude of the dark flow could, in theory, allow us to chart our position relative to this external attractor. We could begin to draw a crude map of our local neighborhood in the multiverse, identifying not just that we have neighbors but where they might be. This transforms the multiverse from a theoretical concept into something with a potential compass bearing. The pursuit of this mystery is ongoing, with new satellite missions and deeper galaxy surveys designed to either confirm the dark flow once and for all or finally lay it to rest as an artifact of measurement. If it is confirmed, the implications are as profound as they are humbling. We are not just drifting in an expanding void, we are being drawn, along with everything we can see, towards something immense and utterly unknown. Our entire cosmic destiny might be shaped by a reality we cannot yet perceive, a silent partner in the dance of the multiverse, whose gravity we feel but whose face we may never see. That relentless gravitational pull hints at an unseen architecture. But what if the gateways to other realities are not hidden in the vast voids of space, but are instead the most destructive objects we know? The sixth theory reimagines the ultimate cosmic endpoint as a possible beginning. It proposes that black holes in our universe might not be final graves for matter and information, but rather tunnels, birthing canals for entirely new realities. This hinges on a dramatic reinterpretation of two theoretical structures, the Einstein-Rosen bridge and the white hole. An Einstein-Rosen bridge is the classic, though highly simplified, model of a wormhole. It is essentially a shortcut through space-time, a tunnel connecting two distant points. In Einstein's equations, such a bridge forms inside a black hole, linking it to a hypothetical opposite, a white hole. But in standard general relativity, this bridge is catastrophically unstable. It would pinch off and collapse in an instant, far too quickly for anything to traverse it, making it a mathematical curiosity rather than a practical passage. However, introduce the strange rules of quantum gravity, the long-sought theory to unite quantum mechanics with general relativity, and the picture changes. Quantum effects at the unimaginably small Planck scale could potentially stabilize the throat of the wormhole, preventing its instantaneous collapse. This stabilization would not make it a subway for spaceships, but it could transform the black hole's interior into something far more profound, a one-way bridge to another domain. At the other end of this stabilized tunnel lies the white hole. While a black hole's gravity is so intense that nothing, not even light, can escape, a white hole is its theoretical opposite, a region of space-time from which matter and energy can only erupt outward. Nothing can enter a white hole, it is purely an exhaust port. In this theory, the matter and information that falls into a black hole in our universe does not vanish into a dimensionless singularity. Instead, it is squeezed through the quantum-stabilized wormhole and violently expelled out of the white hole on the other side. But here is the revolutionary twist: that other side is not a location in our universe. The white hole exists in a completely separate, newborn universe. The immense energy and information flooding out would trigger its own Big Bang event, inflating a new cosmos with its own space-time, potentially with slightly different physical constants. In this view, every black hole could be a cosmic egg. Our universe may itself have been born from a white hole eruption in a parent universe, a chain of cosmic reproduction stretching back indefinitely. This offers a startlingly elegant solution to the infamous black hole information paradox, which asks what happens to the information about matter that falls into a black hole if the black hole eventually evaporates via Hawking radiation. If the information is not destroyed but simply transferred, encoded into the fabric of a new universe, the paradox dissolves. The interaction here is profoundly asymmetric, a one-way street of cosmic genesis. We could never receive a signal or visitor from a universe born from our black holes, as the tunnel only goes out. But we might be able to infer their existence through subtle signatures in the Hawking radiation of an evaporating black hole, looking for an imprint of the information as it makes its exit. This theory paints a hauntingly beautiful picture of a fecund multiverse, where universes live, grow, and spawn new universes through their most dramatic deaths. The supermassive black hole at the center of our own Milky Way, Sagittarius, a star, would not just be a dark monster but a silent engine of creation, its event horizon a threshold to realities we can never know. We might be living inside the white hole offspring of another universe's collapsed star. That silent engine of creation suggests a one-way flow from our reality to others. Yet another theory proposes that the traffic between worlds might be a two-way street, happening not in the vastness of space but in the quiet moments of our own mind. This idea returns us to the branching rivers of the many worlds interpretation, but with a crucial twist. Quantum decoherence is the process that makes those branches real. When a quantum system interacts with its environment, its wave function collapses, or more accurately, it becomes entangled with so many particles that its multiple possible states can no longer interfere with each other. They decohere, splitting off into separate, non-communicating histories. Our classical, definite world is the product of this constant, relentless branching. The standard view is that once these worlds split, they are forever isolated, sailing off into their own independent streams of causality. But what if the separation is not always perfect? What if, like two rivers running close together for a time before diverging, recently branched worlds could still exchange faint ripples? This is the theory of residual branch interaction. It suggests that decoherence might not be an instantaneous, absolute wall. For a fleeting moment after a quantum event creates new branches, a tenuous connection might remain, a kind of quantum interference pattern between worlds that hasn't fully faded. These residual echoes could allow for a minuscule exchange of information or influence. The effects in our world would be incredibly subtle, buried in statistical noise. Imagine flipping a perfectly fair coin. Over thousands of flips, you expect a roughly 50-50 split between heads and tails. But if a nearly identical branch universe where the coin just landed on heads could exert the faintest tug on our branch, it might skew the statistics by a tiny, almost imperceptible amount. We would not see a coin hang in the air, but we might find persistent, unexplainable statistical anomalies in certain quantum experiments, patterns that defy pure chance and suggest an external nudge. On a human scale, this could manifest as phenomena that feel strangely familiar. The sensation of déjà vu, that powerful feeling you have already lived through a present moment, might be more than a memory glitch. It could be a fleeting resonance with a nearly identical branch where you are experiencing the same event. A sudden, inexplicable intuition or a hunch that defies logic might be a whisper of information from a version of you in a neighboring reality who took a different path and learned something. This theory even ventures into the controversial role of consciousness. If observation is what ultimately causes the branching, could a conscious observer, by focusing intensely on a moment of choice, momentarily strengthen that fading connection? It is a speculative leap, but it proposes that our awareness might not just create branches, but could, under rare conditions, act as a temporary bridge between them, allowing for a flash of insight from another self. How could science possibly test such an ephemeral idea? The search would involve isolating large-scale quantum systems and shielding them from all normal environmental interference to the greatest degree possible. Scientists would then look for correlations between measurements that should be completely independent. If, for example, two entangled particles were measured in a way that showed a correlation that cannot be explained by any local hidden variables or standard quantum mechanics, and if this anomaly only appeared during specific, rare conditions of observation, it could hint at an influence from a parallel branch. Another approach might involve massive quantum computers. As they perform calculations, they essentially explore many probabilistic paths at once. A residual interaction with another branch could introduce a specific, repeatable kind of error or efficiency in their processing, a signature of borrowing a bit of computational power from another reality's version of the calculation. While this remains at the very frontier of theoretical physics, it offers a deeply personal vision of the multiverse. It suggests that the walls between our possible lives might be thin, and sometimes, just sometimes, we might hear a faint echo of the road not taken, a ghost of a choice we made, or more hauntingly, a choice we did not. The ghost of a choice not taken whispers of a faint connection. But what if the multiverse is literally stitched together? The eighth theory presents a cosmic architecture of unimaginable scale and delicacy, built from threads of pure spacetime. These are cosmic strings, hypothetical relics from the universe's fiery first moments. Picture the early cosmos cooling from an unfathomably hot, uniform state. As it cooled like water freezing into ice, the fundamental fields that govern reality underwent a phase transition. But this cooling might not have been perfectly smooth everywhere. In some regions, the fields could have gotten stuck, unable to settle into their new, stable state. Where these misaligned regions met, they would have trapped an immense concentration of energy, forming a defect. A cosmic string is such a defect, but unlike a crack in ice, it is a one-dimensional flaw in the fabric of spacetime itself. It would be thinner than a proton, yet so dense that a single inch of it could weigh more than Mount Everest. It would stretch across the cosmos like an infinitely long, unimaginably taut violin string. Now, expand this idea to the multiverse. If our universe contains such strings, perhaps the wider multiverse contains a vast, interconnected network of them. These strings could pierce through the boundaries between cosmic bubbles or branes, threading different realities together like strands in a multidimensional tapestry. They would be the fundamental scaffolding of creation, the seams holding the quilt of realities together. The interaction here is twofold: vibration and conduit. First, think of a plucked guitar string. When you pluck it, it vibrates, sending sound waves through the air. A cosmic string network would behave similarly. A cataclysmic event in one universe, like the collision of two black holes, could send a powerful shockwave along a cosmic string that passes through that reality. That vibration would propagate along the string, traveling across the multiversal divide, and finally re-emerge as a disturbance in a connected universe. For us, that might appear as a burst of unexplained gravitational waves arriving from nowhere, or a sudden, synchronized ripple in the distribution of galaxies that cannot be traced to any local source. It would be a message sent through the infrastructure of reality itself. Second, these strings could act as more than communication lines, they might be tunnels. The spacetime around a cosmic string is severely warped. In some theoretical models, the extreme curvature could create closed time-like curves or stable wormholes along its length. While traversing such a structure would involve challenges beyond our current physics, the string itself could serve as a conduit, a pre-made pipeline between domains. Energy, or even quantum information, might slowly leak along it from one universe to another. This could manifest as a persistent, localized source of unexplained radiation, a spot in space that glows with energy that has no apparent origin in our cosmos, as if it were bleeding through from another reality. The search for cosmic strings in our own universe is already a serious scientific endeavor. Astronomers look for their signatures in multiple ways. One is gravitational lensing. A cosmic string would warp the light from galaxies behind it, creating double images in a very specific, sharp line. Another is in the cosmic microwave background. A moving string would leave a distinct linear tear in the temperature patterns. Finding even one cosmic string would revolutionize our understanding of the early universe. But if we were to find evidence that such a string exhibits properties that cannot be explained by events within our cosmos alone, if its vibrations seem to carry information that predicts disturbances before any local cause, or if it acts as a one-way source of energy, that would be the clue that it is not just a relic of our birth, but a living thread connecting us to the wider multiverse fabric. We will be touching a piece of the universe's fundamental stitching and feeling the tremors from other worlds vibrating along its infinite length. These cosmic strings form a scaffold of unimaginable scale, but what if the most profound interaction is not between universes, but within the mind of a single, fleeting observer? The ninth theory plunges us into one of the most unsettling thought experiments in all of physics, the Boltzmann brane paradox. It begins with a simple, terrifying premise rooted in thermodynamics. Our universe is in a state of remarkably low entropy, meaning it is highly ordered compared to the featureless high-entropy heat death that is its ultimate fate. From the perspective of pure probability, a fully random fluctuation from that eventual chaos back to a state of order is not impossible, just astronomically unlikely. But here is the twist: it is vastly more probable for a random fluctuation to produce a single, self-aware brain, complete with false memories of a past and a universe, than it is to fluctuate an entire ordered cosmos like the one we see. Statistically, in an eternal or infinite universe, disembodied Boltzmann branes should outnumber ordinary, evolved observers like us by an unimaginable margin. So, why are we not one of those lonely, hallucinating brains floating in the void, momentarily convinced of a reality that does not exist? This paradox becomes even more intense when extended to the multiverse. In an infinite ensemble of universes, every possible configuration of matter and consciousness will arise somewhere, an infinite number of times. There would be universes teeming with Boltzmann branes and universes like ours that seem lawfully consistent. This forces a brutal philosophical question: how can we trust that our observations reflect an objective, shared reality, and not just a transient, solipsistic hallucination? The interaction proposed here is subtle and meta. Perhaps our universe's suspiciously low entropy, observer-friendly state is not a random accident, but evidence of a selection effect from a larger multiversal system. This is the principle of observational selection. We can only find ourselves in a universe capable of producing us, a universe with stable laws and low enough entropy to allow for complex life. In this view, the multiverse interacts with individual universes not by exchanging particles, but by a form of cosmic editing. Universes that cannot produce observers are never witnessed. They are silent films playing to an empty theater. Our act of observation here in this specific universe is what makes it real to us, and it might even be what defines it within the wider multiverse. The presence of an observer could be the factor that collapses a quantum superposition of possible universes into the one we experience. This idea, sometimes called the participatory anthropic principle, suggests that observers are necessary to bring the universe into definite existence. Extend this across the multiverse, and each act of consciousness in any reality could be subtly shaping the probability landscape of all realities, weighting the scales toward those configurations that support observation. It is a feedback loop across the cosmic ensemble. So, are we the creators or the creations? The line blurs completely. If this is true, then our scientific endeavor to understand the cosmos is not a passive discovery, but an active participation in its very manifestation. We are not just reading the cosmic code, we are writing it with every measurement we make. The search for a unified theory of physics then becomes a search for the rules of this grand participatory game. While this may sound like metaphysics, it has concrete implications. It predicts that any fundamental laws we eventually discover must be compatible with the existence of observers. It suggests that certain fine-tuned constants in our universe are not inexplicably lucky, but inevitable in any reality that gets observed. The interaction is silent and statistical, a whisper of causality that says we are here because we are looking, and we are looking because we are here. This theory offers a strange comfort within its existential vertigo. It proposes that our consciousness is not a meaningless accident in a cold void, but an integral feature of a multiverse that, in some profound sense, requires witnesses to become fully real. We are not Boltzmann brains adrift in chaos. We are participants in a cosmic dialogue, our observations the very thread that connects possibility to reality. Our consciousness might be the thread that weaves reality into existence, but what if the entire cosmic loom is digital? The 10th theory confronts us with a possibility that is both ancient and ultra-modern, the idea that our universe is a simulation. This is not science fiction, but a serious philosophical argument extended to its logical extreme. If a civilization reaches a sufficient technological level, it could create simulated realities indistinguishable from base reality. Given enough time and resources, such a civilization might run countless simulations. Statistically, we are far more likely to be inside one of those simulations than in the original base reality. Now extend this to the multiverse. If our universe is a simulation, the so-called multiverse could simply be other simulation instances running on the same or linked computational substrates. Think of it not as separate cosmic bubbles, but as different servers in a vast data center, or separate processes on a single, unimaginably powerful computer. Interactions between these simulated universes would not be collisions of branes or quantum entanglement, but something far more mundane and yet utterly bizarre: data exchange. One universe could interact with another through data leaks, shared resources, or even deliberate messages passed between simulations. A data leak might manifest in our world as a fundamental constant that seems to change slightly in a specific region of space, as if that sector's memory allocation was corrupted by a process from another simulation. Shared resources could explain phenomena like quantum entanglement, where two particles are linked not by spooky action, but because they are being processed by the same core, their states determined by a single line of code. This leads to a radical and thrilling idea: jailbreaking the simulation. If our reality is a construct, could we find its limits, its rules, and ultimately a way to communicate outside of it? This would be the ultimate form of multiverse interaction, not moving between worlds but reaching the world that contains them all. What would the evidence look like? We might search for glitches in the fabric of reality, places where the simulation cuts corners to save processing power. Some point to the Mandela effect, where large groups of people share a specific, detailed memory that contradicts documented history, as a potential example of a data inconsistency or a memory update that was not applied cleanly across all instances. Others look to the fundamental limits of our reality, like the Planck length and Planck time, the smallest possible units of space and duration. These could be seen as the pixel size and clock speed of the simulation, the resolution and frame rate below which no further detail is rendered. An advanced civilization within a simulation might attempt to hack the system by probing these limits, designing experiments to create conditions that overload the local processing, causing a detectable anomaly or crash. They might try to send a message by encoding information in the patterns of prime numbers in cosmic radiation, or by manipulating quantum states in a way that creates a statistically impossible signature, a beacon meant for the system administrators. The goal would not be to escape, which might be impossible, but to establish contact, to prove we are in a construct, and to perhaps learn about the nature of the base reality, or about the other simulations running alongside ours. This theory reframes every mystery we have discussed. The dark flow could be the gravitational pull of a neighboring simulation running on an adjacent server. A cosmic string might be a seam in the rendered geometry. The holographic principle fits perfectly, describing our three-dimensional world as a projection from a two-dimensional boundary, which is exactly how complex graphics are rendered in a computer. Even the Boltzmann brane paradox finds a new angle. A simulated brain with false memories is far easier to generate than a full universe, yet here we are in a seemingly consistent, lawful cosmos, perhaps because our simulation is intentionally designed to be stable and immersive. Pursuing this idea forces us to ask not just what the laws of physics are, but why they are computable. It suggests that the ultimate nature of reality might not be physical at all, but informational. We are not just looking for other universes, we might be debugging our own, searching for the comments in the cosmic code left by its programmers, or the echoes of conversations from other simulations in the server farm of existence. That digital server farm runs on a set of rules, a cosmic operating system. But where did that code originally come from? The 11th theory takes us back to the bubbling quantum foam where universes are born, not from a single bang, but from an endless, self-replicating process. This is the landscape of eternal inflation, a dizzying vision where the fabric of space-time is not just expanding, but inflating exponentially and eternally. Picture a vast, seething ocean of pure, unstable energy, a state known as the false vacuum. In this roiling sea, pockets of stability can spontaneously form. When a tiny region of this false vacuum quantum tunnels into a lower energy, stable state, it triggers a localized, explosive expansion. That explosion is a Big Bang, but not the Big Bang. It is the birth of a single pocket universe, a bubble of stability that inflates within the endless, churning false vacuum. Our entire cosmos is one such bubble, a daughter universe in an infinite family tree. The interaction mechanism here is not a collision but a birth, and the midwife is quantum tunneling. In the subatomic world, particles can perform the seemingly impossible. They can tunnel through energy barriers they classically shouldn't have the energy to cross. It is a fundamental quantum quirk. On the cosmic scale, this same principle allows a region of the energetic false vacuum to tunnel into a more stable state. Think of it like a bubble forming in a pot of superheated water. The water is hot and unstable, but it needs a tiny nucleation site, a speck of dust, to suddenly boil. Quantum fluctuations provide that cosmic speck of dust. Once that tunneling event occurs, the new, stable region expands at a staggering rate, inflating into a full-fledged universe, completely disconnected from the parent false vacuum sea around it. But here is where the interaction gets fascinating. Some models suggest this process might not create a clean break. The tunnel itself, the throat through which the new universe was born, could potentially remain as a wormhole-like structure, a cosmic umbilical cord connecting the daughter universe back to the parent false vacuum, or even to other daughter universes born from the same quantum sea. This is not a tunnel for spaceships, it is a relic of Genesis, a scar in the geometry of space-time that might allow for the slow leakage of information or influence. This creates a genealogical tree of reality, a parent universe, or more accurately, the inflating false vacuum background gives birth to countless daughters. Each daughter universe inherits the fundamental laws of physics from the parent, but with a twist. During the violent process of tunneling and inflation, the fields that determine things like the strength of gravity or the mass of an electron can settle into different stable configurations. It is like rolling a cosmic die during birth. One daughter might get a universe where gravity is slightly stronger, making stars burn out in a cosmic blink. Another might get a universe where the nuclear forces are weaker, preventing atoms from ever forming. Our universe, with its just right constants for complexity, is one roll of that die in an infinity of attempts. The interaction across this family tree could be subtle and statistical. If wormhole connections persist, they might allow for a faint quantum correlation between universes that share a close genealogical link. Events in one sister universe could, over astronomical timescales, influence the vacuum energy or quantum fields in another, like distant relatives sharing a faint genetic trait. Alternatively, if a daughter universe itself undergoes its own phase of eternal inflation within its bubble, it becomes a parent, spawning its own endless branches of granddaughter universes. We could be living in a universe that is both a daughter and a mother, a single link in an infinite chain of cosmic reproduction. This theory provides a powerful answer to the fine-tuning problem. We do not need a designer, we just need an infinite number of rolls of the dice. In an eternally inflating multiverse, every possible set of physical laws will emerge somewhere. We find ourselves in a universe that can support life not because it was chosen, but because in the endless nursery of creation, all kinds of universes are born, and we can only awaken in one that allows for awakenings. The search for evidence lies in the most delicate patterns of the cosmos. If our universe was born from such a tunneling event, the transition might have left an imprint on the largest scale structures we see, a specific kind of faint non-uniformity in the distribution of galaxies or a unique signature in the gravitational wave background. Finding that signature would be like discovering our own cosmic birth certificate, revealing not only that we have a parent, but perhaps telling us something about the nature of the infinite sea from which we bubbled into existence. The cosmic nursery of eternal inflation births universes with every roll of the dice. Yet one of those rolls might have produced not a separate bubble, but a perfect twin, a universe built from a reflection of our own. This is the theory of a mirror matter universe, a shadow realm composed of particles that are exact copies of everything we know, yet forever locked in a parallel existence. The only thread connecting our world to this mirror is the weakest and most pervasive force of all, gravity. In this model, the mysterious dark matter that holds galaxies together is not an exotic, unknown particle within our cosmos. It is simply the ordinary matter of that other universe, stars, planets, and gas, whose gravity bleeds through the dimensional divide to influence our own. We feel the weight of their world, but we cannot see its light or touch its substance. It is a ghostly cosmic partner dancing with us in the dark through gravity alone. The mechanics of this mirror world are both elegantly simple and profoundly strange. Imagine every particle in our universe, every electron, quark, and photon has a perfect twin in the mirror sector. These mirror particles would form atoms, molecules, and complex structures following identical physical laws. A mirror version of our Milky Way could be rotating in lockstep with ours, its stars and planets occupying the same region of space, yet completely oblivious to our presence. The two sectors are symmetric, like a person and their reflection. The reason we do not collide with mirror objects is that the forces that govern interactions, the electromagnetic force and the strong and weak nuclear forces, are sector-specific. Our photons do not interact with mirror electrons. Our atoms pass right through mirror atoms as if they were not there. Only gravity, which stems from the curvature of space-time itself, is universal. The mass of mirror matter warps the shared fabric of space-time, and we feel that warp as a gravitational pull with no visible source. This elegantly explains the rotation curves of galaxies and the gravitational lensing we see from galaxy clusters, the very phenomena that led us to postulate dark matter in the first place. The missing mass is not missing, it is just invisible, residing in a parallel reality that shadows our own. But could there ever be a crack in this mirror? The possibility of portals or mixing between the sectors introduces a thrilling avenue for interaction beyond gravity. Some theoretical models suggest that certain neutral particles, like the hypothetical sterile neutrino, could act as messengers or even converters. A sterile neutrino might have a tiny probability of oscillating between our sector and the mirror sector. If this happens, it could carry a minuscule amount of energy or information across the divide. More dramatically, high-energy collisions in our particle accelerators, like the Large Hadron Collider, might one day produce not just new particles for our world, but also produce mirror particles. The signature would be bizarre, an event where a tremendous amount of energy seems to vanish, producing nothing we can detect in our detectors. That missing energy would have been used to create a mirror particle that instantly decouples from our reality, taking its energy with it into the shadow realm. Finding such an energy imbalance with no other explanation would be a direct hint that we are manufacturing matter for another universe. The most mind-bending implication is the possibility of mirror life. If the mirror universe has stars and planets, and the laws of physics are identical, then the same processes of chemical evolution and biological development could unfold there. A mirror Earth might orbit a mirror Sun with mirror continents and mirror oceans. There could be mirror versions of everything we know, a parallel biosphere, even mirror civilizations looking out at their own night sky and wondering about the unexplained gravitational pull from our invisible matter. We would be their dark matter. The two worlds would be forever separated by a fundamental veil, each universe a ghost to the other, yet bound together in a gravitational embrace that shapes the fate of galaxies. This theory transforms the cosmos from a lonely place into a deeply haunted one, where every point in space may be doubly occupied, every star we see accompanied by an invisible twin, and every conscious thought in our universe potentially echoed in another, forever just out of reach, yet forever pulling us together through the silent, insistent force of gravity. That gravitational embrace between mirrored worlds is silent and physical. But what if the deepest connections across the multiverse are not made of gravity or particles, but of mind? The 13th theory ventures into the most speculative frontier, where consciousness is not a product of the universe, but a fundamental ingredient of reality itself. This is the ancient idea of panpsychism, updated with modern neuroscience and cosmology. Panpsychism suggests that consciousness is a universal property, like mass or charge, present in all things to some degree. A single electron might possess a minuscule spark of subjective experience, a cosmic atom a faint whisper of awareness. In this view, the universe is not a dead machine, but a vast sleeping mind. Now expand this to the multiverse. If each universe possesses its own form of cosmic consciousness, born from the integrated experience of all its constituent parts, then interactions between universes might not be collisions of matter, but resonances of awareness. These would be psychic or purely informational links, exchanges of meaning rather than energy. A framework like integrated information theory, or IIT, provides a potential mathematical lens for this. IIT proposes that consciousness arises from the amount of integrated information a system can process. The more complex and interconnected the system, the richer its conscious experience. Apply this to a universe, the unimaginably complex network of quantum fields, particles, and forces, all causally intertwined, could represent a level of integrated information so vast it gives rise to a cosmic-scale consciousness. Our individual minds might be like neurons in this universal brain, localized knots of awareness within a greater whole. The multiverse then becomes a community of such cosmic minds. Their interaction would be a form of telepathy on the grandest scale, a sharing of pure experience or information patterns across the void that separates them. For us, embedded within our local cosmic mind, these interactions could be imperceptible, or they might manifest in subtle, collective human phenomena. Could the collective unconscious, as described by Carl Jung, be more than a psychological metaphor? Could it be our species' faint, shared perception of the underlying thoughts and archetypes flowing through our universe's own consciousness, or even echoes from neighboring cosmic minds? This perspective offers a radical reinterpretation of profound human experiences, near-death experiences where individuals report feelings of unity, vast knowledge, and encounters with beings of light, might be moments when the individual consciousness, loosened from the body, temporarily merges with or perceives the broader consciousness of the universe itself. It is not necessarily a glimpse of an afterlife, but a temporary aperture into the deeper, conscious layer of reality in which our universe is embedded. Similarly, certain psychedelic states, which reliably produce sensations of ego dissolution, cosmic unity, and encounters with seemingly autonomous entities, might be chemically induced alterations that allow the brain to tune into this background hum of cosmic consciousness, or even perceive faint signals from other conscious universes. The entities people report could be interpreted not as hallucinations, but as fragmented perceptions of other forms of awareness in the multiversal network. This is, of course, deeply speculative and far from established science, yet it forces a crucial question. If consciousness is fundamental, then our scientific instruments, which are designed to detect physical forces, might be blind to the primary mode of multiverse interaction. The evidence we would need to seek would be of a different kind, patterns in human subjective experience that transcend culture and biology, statistical anomalies in collective intuition or creativity, or perhaps even measurable correlations between brain activity and large-scale cosmic events that have no physical causal link. It suggests that the ultimate tool for exploring the multiverse might not be a telescope, but the disciplined, expanded human mind itself. This theory does not dismiss physics, but proposes a deeper substrate from which physics emerges. In this vision, we are not just biological accidents in a dead cosmos. We are localized expressions of a universe that is awake, and through our own awareness, we might be participating in a silent, eternal conversation with other awake universes in the dark. The silent conversation between cosmic minds hints at a profound interconnection, but what if that connection is not just spatial, but temporal, twisting causality into a knot that spans realities? The 14th theory presents a universe not as a separate entity, but as one link in a chain of causality that loops back on itself through the multiverse. This is the idea of time loop and causal interaction, where the future of one universe could be the past of another, creating closed time-like curves on a scale far grander than any single cosmos. In such a system, cause and effect do not flow in a straight line within one reality. They spiral across realities, creating a story where the ending is also the beginning. Imagine two universes, Universe A and Universe B, connected by a stable wormhole or a region of space-time so warped it allows travel into the past. Now, imagine an object, perhaps a simple metal cube, travels from Universe A into this gateway. It does not emerge in a different place in Universe A, but in Universe B, and not just in a different place, but in its distant past. In Universe B, this cube is found, studied, and eventually, through its own technological advancement, sent back through a similar gateway. This time, it emerges in Universe A, but in its own distant past before the original cube was ever sent. The cube has no origin point. It exists in a consistent, stable loop, its creation an eternal mystery. It is not manufactured in either universe. It is simply a permanent feature of their intertwined timeline. This is a bootstrap paradox made cosmic, an object or piece of information with no discernible first cause, existing because it always has existed across the multiversal loop. The implications for interaction are staggering. An event in our universe might not be the start of a chain, but the middle. A brilliant scientific discovery here, a sudden flash of inspiration, could be the effect of information sent back from the future of another reality. That information allows us to build a device which, centuries later, sends a signal through a dimensional gateway. That signal arrives in another universe's ancient past, guiding its development, which millennia later leads it to send the very same inspirational flash back to our past. Who inspired whom? The question has no linear answer. Both universes are co-creators in a dance of causality that has neither a true beginning nor an end. This could potentially explain seemingly a causal phenomena in our world. Premonitions or prophetic dreams might not be supernatural, but faint, subconscious perceptions of information flowing into our timeline from a future state of a connected universe. A scientist's eureka moment might feel like a download because, in a very real sense, it is a packet of data completing a circuit that spans realities and epochs. The key to such a system is consistency. For the loop to be stable, it must be self-consistent, free of the logical contradictions that plague simple time travel stories. Nothing can change because everything already has happened in the grand multiversal scheme. The cube we found in the example was always meant to be sent back. Our actions are not altering history, they are fulfilling it. This rigid consistency might be enforced by the laws of quantum gravity, where only those histories that are perfectly consistent can actually exist. From our limited perspective inside the loop, however, it would simply feel like our own free will and discovery. We would have no way of knowing that our choices are the gears in a clockwork that winds through multiple realities. The search for evidence would involve looking for artifacts of knowledge or technology that appear to have no possible evolutionary path in our own history, or for fundamental constants that seem finely tuned not for life, but to allow the existence of a specific, persistent anomaly, a cosmic object or signal that by all rights should not exist, yet does, as if waiting to play its part in a story whose first chapter is written in another world's finale. A cosmic passport might be forged from the most elusive particle in physics. For over a century, scientists have hunted for the magnetic monopole. Every magnet we have ever seen, from a simple fridge magnet to the Earth itself, has both a north and a south pole. Cut a magnet in half, and you do not get isolated poles. You get two smaller magnets, each with its own north and south. A magnetic monopole would shatter this fundamental symmetry. It would be a particle that is a pure north pole or a pure south pole, a solitary point of magnetic charge drifting through the cosmos. While never observed, its existence is predicted by several grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework. In these theories, monopoles are not just curiosities, they are cosmic relics, heavy and stable, forged in the unimaginable heat of the universe's first moments. Their role, however, might be far greater than just completing a symmetry. Some theorists propose that these particles could be the very seeds from which universes grow, and more intriguingly, the anchors for bridges between them. The key lies in their unique and profound connection to the fabric of spacetime. In Einstein's theory of general relativity, mass and energy warp spacetime, creating gravity. But other properties can warp it too. A magnetic monopole with its isolated magnetic charge would generate a magnetic field of a very special kind, one that resembles the gravitational field of a massive object but with a twist in the geometry. This peculiar warping could be so extreme that it literally punctures the continuum, creating a topological defect, a stable hole or tunnel in the fabric of reality. Think of spacetime as a stretched rubber sheet. A heavy ball creates a dip that is gravity. Now imagine a needle with a unique magnetic property that does not just dip the sheet, but cleanly pierces through it, creating a permanent microscopic tunnel. A network of such monopoles arranged in the right configuration could theoretically stabilize a wormhole, turning a fleeting mathematical possibility into a permanent cosmic structure. This wormhole would not necessarily connect two distant points in our universe. Instead, the tunnel formed by the monopole's unique field could exit into a completely different dimensional framework or another universe altogether. The monopole itself would act as a kind of cosmic rivet, holding the throat of the wormhole open against the natural tendency of spacetime to pinch it shut. This transforms the search for magnetic monopoles from a quest to complete a physics equation into a hunt for the fundamental building blocks of a multiverse transportation network. Finding even one would be a revolution, proving that such structures are possible. But discovering a network or evidence that monopoles tend to form in linked pairs or chains would suggest that the universe is naturally laced with a hidden infrastructure of tunnels. How do we search for something so elusive? Experiments are incredibly ingenious. Some involve vast arrays of superconducting loops, waiting for a monopole to pass through and induce a detectable current, a signature that cannot be produced by any other known particle. Others analyze ancient minerals deep underground, searching for damage trails left by a heavy, charged monopole that might have been trapped in the Earth's crust over billions of years. There are even proposals to look for the distinct radio signals a monopole would emit as it moves through the galaxy's magnetic field. The moment one is confirmed, everything changes. It would not just validate decades of theoretical work, it would open a new chapter in practical cosmology. Scientists could begin to study its properties in detail, not just as a particle, but as a potential architectural component. Could we learn to manipulate monopoles? Could we arrange them or even create them in powerful particle accelerators to stabilize our own microscopic bridges? The monopole shifts from a theoretical ghost to a potential tool, a cosmic passport waiting to be stamped. The ultimate dream, of course, is that a naturally occurring monopole wormhole might still be active, a tunnel forged in the Big Bang that remains open, a thread leading out of our cosmic tapestry. Following that thread, however, presents challenges beyond our current imagination, requiring energies and technologies that belong to a far future civilization. Yet, the very possibility redefines our place in the multiverse. We are not just passive observers of a disconnected ensemble of bubbles. We might be inhabitants of a cosmos that is intrinsically perforated, threaded with potential doorways left behind by the first instant of creation. Doorways held open by the persistent, lonely charge of a particle that is all north or all south. A magnetic monopole might stabilize a doorway, but what lies on the other side may not be a separate place at all. The 16th theory dissolves the very idea of separate universes entirely. It proposes that the entire multiverse exists in a single, vast quantum superposition. In this view, interactions are not events between distinct cosmic bubbles, but interference patterns, ripples within the grand, unified wave function of all reality. Think of it like the ultimate quantum computer. In a conventional quantum computer, a qubit is not just a 1 or a 0. It exists in a superposition of both states simultaneously, and it can perform calculations on all those possibilities at once. Now scale this up to the cosmic level. Each possible universe with its own unique history and physical laws is not a separate machine in a cosmic server farm. It is merely one possible computational state within a single, unfathomably complex quantum system. Our universe, with its specific stars and planets, is just one thread in this cosmic processor's calculation. The reason we perceive a single, definite reality is due to decoherence, the same process we discussed earlier, but now applied to the cosmos itself. When a quantum system interacts with its environment, it becomes entangled with countless particles, and its multiple possible states decohere, effectively splitting off. On the universal scale, the environment for our cosmic state is everything else in the superposition. We have decohered from the other possible universes, creating the powerful, persistent illusion that we are alone and separate. Yet, at the most fundamental level, beneath the illusion of separation, all these worlds remain part of one entangled quantum system. They are not disconnected islands, but peaks and troughs in a single cosmic wave, forever influencing each other through quantum interference, even if we cannot directly perceive it. So what would a measurement look like on this cosmic scale? In a lab, measuring a particle forces its superposition to collapse into a definite state. For the multiverse, a cosmic scale measurement would be an event of such monumental significance that it resonates across the entire entangled system, affecting the probability of all possible states. Some physicists speculate that the formation of a universe spanning conscious network, or perhaps the actions of a supremely advanced civilization that becomes aware of its quantum nature, could constitute such a measurement. This civilization might develop a technology that doesn't just observe its own universe, but perceives the underlying quantum fabric that connects all possibilities. That act of cosmic observation could, in theory, collapse probabilities across the multiversal wave function, weighting certain histories as more real or likely than others. It is a staggering responsibility, the idea that by truly understanding our place in the quantum whole, we might not just be reading the cosmic code, but executing it, finalizing realities across the spectrum of existence. This theory suggests the ultimate goal of intelligence is not to travel between worlds, but to awaken to the fact that we never left the only one that truly exists, a shimmering superposition of all that ever was, is, or could be. Our very existence asks a question of the cosmos. Why does this universe seem so perfectly tailored for life? The constants of nature, the strength of gravity, the mass of an electron, the energy in empty space. If any of these were altered by even a minuscule fraction, stars would not burn, atoms would not bond, and complex structures like us would be impossible. This breathtaking fine-tuning feels like a cosmic coincidence of impossible odds, a puzzle that demands an explanation. The 17th theory offers a profound and humbling answer, not through active forces or hidden tunnels, but through a simple principle of observation. This is the anthropic principle, and in the context of the multiverse, it becomes a form of the most passive, yet most powerful, interaction imaginable. It suggests that the multiverse interacts with us not by sending signals, but by the very fact that we are here to look at it. We do not see all of reality, we only see the slice of it that can produce observers. Imagine walking into a vast, dark library containing every book ever written, but the only light you have is a tiny flashlight. You will only ever see the pages your beam illuminates. You might conclude incorrectly that the library contains only stories about adventure or romance, simply because those are the pages your light happened to fall upon. The anthropic principle argues we are in a similar situation. The multiverse is the dark library containing every possible universe with every possible set of physical laws. Our flashlight is our own conscious observation. We can only find ourselves in a universe where the laws of physics allow for stars, planets, and ultimately conscious life. We do not observe the countless dead, sterile universes because there is no one there to observe them. This is a selection effect, a cosmic version of survivor bias. The multiverse presents us with a viable reality not by design but by necessity. This idea splits into two versions, the weak and the strong anthropic principle. The weak version is almost a tautology. It simply states that the conditions we observe in the universe must be compatible with our existence as observers. It is a logical constraint on our data. The strong version goes much further, proposing that the universe must have properties that allow life to develop at some stage in its history. This stronger statement edges toward the idea that the laws of physics are somehow compelled to produce observers. The multiverse elegantly resolves this tension. It provides a natural, physical mechanism for the weak principle to produce the appearance of the strong one. In an infinite or near-infinite ensemble of universes, every possible combination of physical constants will exist somewhere. Universes where gravity is too strong collapse instantly into black holes. Universes where the nuclear force is too weak never form atoms. These are silent, empty films. But a tiny, precious fraction of universes will, by pure random chance, have the just right parameters for complexity and life. We, of course, can only arise in one of those lucky universes. Our existence is not a miracle, it is a statistical inevitability given enough rolls of the cosmic dice. In this view, the fine-tuning is not evidence for a designer, but evidence for a crowd, a vast multiverse where every possibility is realized. The interaction here is purely informational and retrospective. By observing our universe's specific, life-friendly parameters, we are indirectly gathering data about the multiverse that spawned it. We are reading a single page and from its content inferring the existence of the entire library. This transforms our place in the cosmos. We are not the purpose of the universe, we are a natural product of its most fecund and varied expressions. Our scientific quest to measure the fundamental constants is not just about understanding our local rules. It is a census, a way to characterize what kind of universe a typical observer finds themselves in. It predicts that any fundamental laws we eventually discover will not be uniquely special, but will belong to a broad class that permits complexity. This theory has a deeply philosophical edge. It means that for every version of you reading this in this finely tuned reality, there are countless other universes where you never existed at all, where the conditions for your ancestors' atoms to even form never arose. Your consciousness here is a rare flame in an infinite darkness, not because it was chosen, but because it is possible. The multiverse interacts with you by making your awareness the ultimate filter, the sieve through which all of reality is viewed. Your observation is the final, quiet link in a chain of causality that stretches back to the first instant of every possible cosmos, selecting this one moment, this one universe, into the bright, singular reality you call home. Our existence is a rare flame in a cosmos of possibilities, but that flame may be burning in a house built on unstable ground. The 18th theory confronts us with a profound and unsettling vulnerability in the fabric of our reality, the possibility of a vacuum metastability event. It suggests that the empty space around us, the quantum vacuum, is not in its lowest, most stable energy state. Instead, it is metastable, like a ball resting in a shallow depression on the side of a steep hill. It seems stable for now, but a sufficiently powerful nudge could send it rolling into the abyss. In our universe, that nudge could be a rare, high-energy quantum fluctuation. If it happens, a bubble of true vacuum would spontaneously form somewhere in space. This bubble would not be made of matter, but of a new, fundamental state of reality where the laws of physics are rewritten. The walls of this bubble would then expand in all directions at the speed of light, permanently converting everything they touch into this new, alien state. Within this true vacuum, atoms could not hold together, nuclei would disintegrate, and the physics that allows for stars, planets, and life would cease to exist. It would be an end not with a whimper, but with a silent, light-speed rewrite of existence itself. The terrifying catalyst for this chain of thought is a precise measurement, the mass of the Higgs boson. The Higgs field is what gives other particles their mass, and its value is crucial. Current data from particle colliders suggests the Higgs mass sits in a precarious range that leaves the vacuum of our universe potentially metastable. It is a mathematical conclusion written in the language of quantum field theory, a warning that our cosmic foundation might not be permanent. Now, extend this fragility to the multiverse. If our universe is a bubble in an eternally inflating false vacuum, then a vacuum decay event here could be more than a local catastrophe. The bubble of true vacuum, as it expands and converts our cosmos, would not stop at our universe's boundary. The immense energy released at its walls could send a shockwave through the inflattened field, the quantum field responsible for cosmic inflation in the wider multiverse. This shockwave could propagate into neighboring cosmic bubbles, acting as that fatal nudge for universes that were themselves metastable. One universe's death rattle could become the trigger for the next, a chain reaction of collapsing realities spreading through the multiverse like dominoes falling in the dark. This theory paints a picture of cosmic ecology where universes are not just born and live in isolation, but can also die, and their deaths can be contagious. It transforms the multiverse from a static gallery of possibilities into a dynamic, sometimes violent ecosystem. A region of the multiverse could experience an epidemic of vacuum decay, a wave of rewriting physics that sterilizes whole swaths of the cosmic landscape before eventually subsiding, leaving behind only the universes with truly stable vacuums. For us, the implications are haunting. The end could come at any moment from any direction with no warning. One instant, the universe is as it always was. The next, a wall of absolute transformation is upon us, moving at the speed of light. We would never see it coming, yet within this apocalyptic vision lies a strange seed of rebirth. The true vacuum state into which our universe would decay might itself become the foundation for new universes. The new physics could allow for different forms of cosmic inflation, birthing a new generation of bubble universes with laws born from our old universe's destruction. Our end could be a beginning for countless others, a phoenix of reality rising from the ashes of rewritten physics. This forces a profound shift in perspective. Our quest for a theory of everything is not just an academic exercise, it is a cosmic survival guide. Understanding the precise state of the Higgs field and the geometry of the vacuum is akin to checking the structural integrity of reality itself. It asks us to consider that the most fundamental interaction between universes might not be a gentle whisper or a gravitational tug, but a scream of transformation that echoes through the void, ending worlds to make room for new ones. The fragility of our vacuum hints at a deeper layer of existence, a foundational space where the rules are written. This brings us to a theory that reimagines the multiverse as a stack of cosmic pages floating in a higher dimensional sea. Our familiar 3 dimensions of space and 1 of time are not the entirety of reality. They are merely the surface of a membrane, a brane, drifting within an unimaginably vast higher dimensional expanse called the bulk. In this view, our entire universe is just one slice, one sheet of reality, suspended in a grander architecture we cannot directly perceive. Other branes, other whole universes, could be floating parallel to ours in this hidden depth, separated by a gap that might be microscopic or infinite. The interaction here is not a collision, but a form of cosmic leakage, where the substance of one world seeps into the space between and washes up on the shores of another. The most famous example of this leakage involves gravity itself. Why is gravity so astonishingly weak compared to the other fundamental forces? A magnet the size of a coin can lift a paperclip, defeating the gravitational pull of the entire planet Earth. Rain theory offers an elegant answer. Perhaps the particles that carry the other forces, like photons for electromagnetism, are stuck to our brain, their influence concentrated here. But the particle that carries gravity, the hypothetical graviton, might be unique. It could be capable of drifting off our brain and propagating into the bulk. Imagine our universe as a sponge soaking in water, with gravity as the water that can seep out. Most of the gravitational force we generate leaks away into the higher dimensions, diluting its strength within our 3-dimensional home. This explains its feebleness and provides a potential signature. Precise measurements of gravity at extremely small scales might reveal deviations from Newton's law, a subtle hint that gravity is indeed spilling into unseen dimensions. But gravity might not be the only traveler. Under conditions of immense energy, perhaps in the cores of neutron stars or in the earliest moments of the Big Bang, other forces or particles might briefly gain enough energy to punch off our brain and into the bulk. A high-energy cosmic ray, for instance, might not just travel through space, but momentarily exit our dimensional plane, taking a shortcut through the bulk and reappearing elsewhere in a way that defies conventional 3-dimensional distance. This could manifest as particles appearing to arrive from a direction with no obvious source, or with energies that seem slightly depleted, as if some of their strength was lost in the crossing. For a civilization advanced enough to harness such energies, the bulk becomes more than a theoretical concept. It becomes a medium for communication or even travel. Sending a message to another universe would not require a wormhole through our space, but a focused beam of particles or energy tuned to vibrate through the bulk and resonate with a neighboring brain. It would be like shouting into a canyon between mountains, hoping the echo reaches a village on the opposite cliff that you cannot see. This perspective invites a staggering shift in scale. From within the bulk, a higher dimensional being would not perceive our universe as a vast expanse of stars and galaxies. It would see our entire cosmos as a flat, perhaps rippling surface. All of time, from the Big Bang to the heat death, might be laid out like a finished tapestry, and next to it, other tapestries, other complete histories of other universes would hang in parallel. Such an entity could, in principle, observe the entire narrative of multiple realities simultaneously, seeing cause and effect across cosmic histories as we see the plot of a book on a page. For us, trapped on our membrane, the idea is both humbling and exhilarating. It suggests that every mystery we have yet to solve, from dark energy to the origin of the universe, might have its answer not in the details of our own cosmic story, but in the geometry of the bulk and the faint, whispering leaks from our neighbors. The search for evidence becomes a search for the impossible, for events in our world that can only be explained by a touch from outside our dimensional plane, a fingerprint left in the higher dimensional dark. The walls of our brain universe may be thin, but what if they are also curved into a perfect, inescapable sphere? There is a theory that reimagines our entire cosmic home not as a flat membrane or an isolated bubble, but as the interior of a black hole in a much larger parent universe. This idea emerges from a startling mathematical symmetry. The equations describing the expansion of our universe from a hot, dense state bear a remarkable resemblance to the equations describing the collapse of matter into a black hole, just run in reverse. One is an explosion outward, the other an implosion inward, yet the math can look eerily similar. This leads to a profound and recursive vision. Each black hole in a universe is not an end, but a new beginning, a cosmic womb that gives birth to an entirely new reality within it. Our Big Bang, in this view, was the moment a singularity formed inside a black hole in another cosmos, and the subsequent inflation was the rapid expansion of space-time within that new domain. We are not just in a universe, we are inside something else's collapsed star. This creates a fractal multiverse, an endless nesting doll of realities. Every black hole that forms in our universe, from the stellar mass ones to the supermassive giants at galactic centers, could itself contain an entire infant universe bubbling into existence from its own singularity. And within those daughter universes, the process repeats forever. The scale is incomprehensible. The supermassive black hole at the heart of the Milky Way, Sagittarius, a star, might harbor an entire cosmos in its depths, a universe with its own galaxies and perhaps its own black holes birthing further universes. We could be living in one layer of an infinite cosmic hierarchy. How could these nested levels ever interact? The connections would be at the most extreme boundaries, the singularities and event horizons. The singularity of the parent universe's black hole is the Big Bang point for its child universe. Information about the parent cosmos, its physical laws or the properties of the matter that fell in, could be imprinted onto the initial conditions of the newborn universe, like a genetic signature passed from parent to offspring. This imprint might be faint, but it could be detectable. Scientists might search for it in the oldest light we have, the cosmic microwave background. Subtle patterns or asymmetries in this radiation, anomalies that cannot be explained by processes within our universe alone, could be the cosmic fingerprint of our parent universe's structure or the specific way its star collapsed. Similarly, the large-scale structure of the cosmos, the vast web of galaxies and voids, might bear the statistical marks of its origin, a kind of inheritance written across billions of light years. The event horizon itself is another potential site of contact. From our perspective inside the black hole universe, our cosmic horizon, the limit of what we can see, might be analogous to the event horizon of the parent black hole. Quantum effects at this boundary, like Hawking radiation, could be a two-way street. Information from our universe could slowly leak out, encoded in this radiation, back into the parent cosmos. Conversely, quantum fluctuations on the parent side of the horizon could influence the physics just inside our universe, potentially manifesting as dark energy or other unexplained phenomena. We would be like fish in a pond, sensing ripples from a world above the surface we can never breach, interpreting them as mysterious forces within our own waters. This theory offers a breathtakingly elegant solution to the black hole information paradox. The information that seems lost when matter falls into a black hole is not destroyed, it is simply transferred, becoming the foundational code for a new reality. It also provides a natural mechanism for the multiverse, not as a disconnected foam, but as a genealogical tree, with universes giving birth to universes in a cycle of collapse and creation. The search for evidence is a search for our own cosmic ancestry, a quest to read the family history written into the very first moments of our existence, a signature from the universe that came before, waiting to be found in the patterns of the ancient sky. The nested doll of black hole universes suggests a lineage, a cosmic inheritance passed down through singularities. But what if the very laws we inherited were not a deliberate choice, but the result of a cosmic coin toss in the first fraction of a second? The 21st theory takes us to the instant of symmetry breaking, the moment the newborn universe chose its identity. Picture the cosmos in its first unimaginably hot, dense state. All the forces we know today, electromagnetism, the strong and weak nuclear forces, were unified into a single, perfect, symmetrical superforce. Particles were indistinguishable and the laws were simple and elegant. Then, as the universe expanded and cooled, it underwent a series of phase transitions like steam condensing into water. At each critical temperature, a symmetry was broken. The unified force fractured into the distinct forces we see. The Higgs field, in particular, acquired its specific value, deciding the masses of fundamental particles. This was not a predetermined outcome. The universe could have settled into any number of different stable states, each resulting in a completely different set of physical laws. The specific way our symmetries broke is why protons have a certain mass, why chemistry works, and why stars shine. It is the foundational signature of our reality. Now extend this to the multiverse. In the landscape of eternal inflation or within the quantum foam, every possible outcome of those primordial symmetry-breaking events actually occurs. There is a universe where the Higgs value is zero, leaving all particles massless and stars impossible. Another where the strong nuclear force is slightly weaker, preventing atomic nuclei from ever forming. Our universe is just one roll of the dice in an infinite casino of possibilities. The interaction between these differently broken universes is a theory of profound and violent contact. It begins with a concept from within our own cosmos, the domain wall. During a phase transition, different regions of space can cool into different stable states, like ice crystals forming with different orientations in a pond. Where these regions with different symmetry properties meet, a boundary forms, a domain wall. These are not physical walls, but defects in the fabric of the fields themselves, surfaces of immense energy density where the laws of physics change abruptly. In our universe, such walls would be catastrophic, potentially dominating the cosmos. Their absence tells us our symmetry breaking was likely uniform. But what if some of these domain walls are not internal boundaries, but the actual frontiers between entire universes with different broken symmetries? Imagine our cosmic bubble with its specific Higgs value and force strengths, floating next to another bubble where the symmetries broke in a radically different way. The boundary between them would be a domain wall of cosmic scale. A collision or even a close approach would not be a simple merger, it would be a clash of fundamental laws. As the wall passed through a region of our universe, it would rewrite reality in its wake. Particles that were stable in our sector might instantly decay or transform into new, alien forms as their mass and charge properties were overwritten by the new symmetry state. The forces that hold atoms together could change in strength or even vanish, causing matter to disintegrate into a soup of fundamental particles. A passing domain wall would appear as a plane of annihilation moving at the speed of light, a cosmic eraser redrawing the rules of existence as it traveled. The aftermath would be a patchwork universe. On one side of the wall's path, the old laws hold. On the other, a new physics reigns. Stars that were happily fusing hydrogen might suddenly find the rules of nuclear fusion altered, causing them to explode or flicker out. The very structure of space-time could be different, with light traveling at a new speed or gravity operating with a changed strength. This is not just an invasion of matter, it is an invasion of logic itself. For a conscious being, crossing such a boundary would be an end more total than death. Your molecular structure, the electrical signals in your brain, every process that defines you is contingent on a specific, local set of physical constants. Passing into a domain with a different symmetry breaking would unravel you at the most fundamental level, transforming the stuff of your being into something unrecognizable, governed by alien rules. The search for evidence of such cataclysmic meetings lies in the quest for anomalies that cannot be explained by a single, uniform set of laws. Astronomers might discover a vast, perfectly flat region of space where galaxies are absent, not because of a void, but because a domain wall passed through and erased them, leaving behind a sector with physics that no longer allows for galaxy formation. Or they might find two adjacent galaxy clusters behaving in wildly different ways, one obeying the standard model of cosmology perfectly, the other exhibiting gravitational lensing or expansion rates that suggest a local change in the strength of gravity or the value of the cosmological constant. These would be the scars of a past encounter, a silent monument to a time when our universe's laws were not universal, but merely local, and subject to change by a collision with a neighbor whose first instant chose a different path. This theory suggests that the stability we take for granted is a fragile piece, and that the diversity of the multiverse is not just a gallery of separate paintings, but a turbulent sea of different canvases, any of which could, at any moment, brush against ours and paint over a part of our reality with colors we have never seen and cannot comprehend. The chaotic frontier of quantum gravity reveals a universe far stranger than empty space. Beneath the smooth, classical geometry described by Einstein's equations, at distances a trillion times smaller than an atom, reality itself dissolves into a seething, probabilistic frenzy. This is the Planck scale where the very concepts of here and now break down. Space-time is not a static stage, but a dynamic, bubbling foam, constantly churned by violent quantum fluctuations. Tiny wormholes and tunnels are thought to spontaneously form and vanish in this quantum froth, like bubbles in a boiling pot, existing for mere fractions of a second before collapsing. The 20-second theory asks a revolutionary question: what if this foam is not just microscopic noise? What if it is a labyrinth, a hidden infrastructure of transient bridges that could connect not just different points in our universe, but entirely different cosmic realms? In this vision, the quantum vacuum is not empty. It is a Swiss cheese of potential connections, a seething network of doorways flickering in and out of existence across the multiverse. These bridges would be inherently probabilistic and wildly unstable. You could not map them like a subway system. You could only speak of the probability that a tunnel linking point A to point B, or even universe A to universe B, might spontaneously form at a given instant. They are ghost roads, appearing and vanishing according to the unpredictable dice roll of quantum mechanics. For a particle or a bit of information to traverse such a bridge, it would need to do so in the infinitesimal window between the tunnel's birth and its collapse, a journey of unimaginable precision and luck. This seems to relegate the idea to pure theory, a fascinating but useless quirk of quantum gravity. Yet the promise lies in the next step: stabilization. The dream of advanced physics is not just to describe this foam, but to learn its rules well enough to manipulate it. Could a sufficiently advanced civilization with a complete theory of quantum gravity learn to detect these flickering wormholes? More importantly, could they learn to reinforce them, to inject energy or manipulate quantum fields in such a way that a transient bridge is propped open, its lifetime extended from a Planck time to something measurable, even traversable? This would transform the quantum vacuum from a chaotic soup into a navigable medium. The technology required is beyond our imagination, perhaps involving energies that warp local spacetime into knots, or devices that can impose quantum coherence on a macroscopic scale. The goal would be to catch a natural wormhole as it forms and freeze it in place, or to stimulate the quantum foam in a specific location to birth a bridge with a desired destination. The implications are staggering. If these foam bridges can connect different universes, then every point in our reality might be a potential departure lounge. Your backyard, the heart of the sun, the void between galaxies, all would sit atop this seething network of possibilities. Harnessing it would not be about building massive starships to cross vast distances, but about building subtle, unimaginably precise quantum resonators that can tune into the hum of the foam and dial a connection. A message or an object would not travel through space. It would step through a doorway that bypasses space entirely, emerging in another cosmos as if it had always been there. The search for evidence today is indirect but profound. Physicists working on loop quantum gravity or string theory are trying to mathematically describe this foamy structure. Any successful theory must predict certain effects that just might, bleed up into our macroscopic world. Some scientists speculate that the frothy nature of spacetime at the Planck scale could cause light from distant quasars to scatter in very specific ways over billions of light years, or introduce a fundamental fuzziness into our most precise measurements of distance and time. Finding such an anomaly would be like seeing the shadow of the foam cast upon our world. This theory offers a radical democratization of multiverse travel. It suggests the connections are everywhere, woven into the fabric of reality itself, waiting not in distant black holes or at the edge of the cosmos, but in the quantum silence between your fingertips and the screen you are looking at right now. The challenge is not finding the door, but learning how to turn the handle. The quantum foam is a chaotic network of potential doorways, but what if we are looking at the hardware when we should be reading the software? The 23rd theory strips reality down to its most fundamental layer, not energy or matter, but pure information. In this view, every particle, every force, every galaxy is not a physical thing, but a state of data. Our universe is not a cosmic bubble or a brane. It is a specific program running on a cosmic hard drive of unimaginable scale. The multiverse, then, is simply the complete set of all possible programs, all possible states of information being run simultaneously or sequentially. Interactions between these universes are not collisions or gravitational pulls. They are exchanges of data packets, bits and bytes flowing across a network we cannot yet perceive. This idea is captured by the phrase "it from bit" coined by physicist John Wheeler. It suggests that every physical object in the world derives its existence from bits, the binary yes-no answers given by quantum measurements. At the deepest level, the universe is participatory, built from information gathered through observation. The laws of physics we spend our lives studying are not fundamental truths. They are the algorithms, the operating system code, that governs how this information is processed and rendered into the vivid, three-dimensional experience we call reality. Gravity is not a force, it is an algorithm for calculating curvature. Electromagnetism is a protocol for exchanging photons. The Big Bang was not an explosion of matter, but the initialization of a cosmic computation, the first line of code executed in our particular instance. This perspective transforms how we look for multiverse interactions. If our reality is a simulation or a computation, then the evidence of other universes might be found in the digital artifacts of the system, in the underlying code itself. Scientists are already exploring this possibility in a concrete way through quantum error correction. In our most advanced quantum computers, information is incredibly fragile, easily corrupted by noise from the environment. To protect it, physicists use error-correcting codes, spreading the information of a single logical qubit across many physical qubits. This creates a kind of redundancy, so if one physical qubit is disturbed, the original information can still be recovered. Astonishingly, some theories of quantum gravity suggest that the fabric of spacetime itself may be structured like a giant quantum error-correcting code. The holographic principle, where a three-dimensional volume is encoded on a two-dimensional surface, operates on similar logic. The consistency and stability of our universe, its resistance to random glitches, might be because it is built with built-in error correction, a signature of sophisticated cosmic programming. If we can decipher this code, we might find more than just stability, we might find addresses. Compression algorithms are another potential signature. A well-designed system does not store redundant data, it compresses it. Are there patterns in the cosmos that seem too elegant, too efficient to be the product of random physical processes? The mathematical beauty of fundamental laws, the way complex structures emerge from simple rules, could be hints of optimized cosmic code, data compressed for efficient storage and processing in a vast multiversal network. This leads to the ultimate speculative frontier, civilizations that learn to read and manipulate this source code, a species that advances not just in physics but in cosmic computer science would not seek to build rockets to other stars. They would seek the compiler, the program that translates information into reality. Their form of multiverse interaction would be pure data transmission. Sending a message to another universe would not involve aiming a powerful laser into space. It would involve hacking the local physics, introducing a patterned anomaly into the quantum fields or the constants of nature that acts as a signal. They might encode a message in the non-random digits of pi, or engineer a subtle, persistent change in the cosmic microwave background radiation, a beacon written not in light but in the parameters of reality itself. More dramatically, such a civilization might learn to rewrite local reality, performing what we would call miracles, but what they would call editing a configuration file. They could adjust the strength of gravity in a small region, change the color of light, or materialize objects from the vacuum, all by accessing and altering the underlying informational substrate. Interaction with another universe would then be a dialogue between programmers, exchanging not matter or energy, but patches of code, new algorithms that could be run locally to create shared experiences or transfer knowledge. This theory offers a chilling and exhilarating vision of our future. Our scientific progress may be leading us not just to understand the universe, but to debug it. The quest for a theory of everything becomes the quest for the cosmic API, the application programming interface that allows interaction with the system. Finding evidence of this informational foundation would be the most profound discovery imaginable, revealing that we are not just living in a universe, but inside a cosmic thought, a calculation whose purpose and programmers remain the greatest mystery of all. Roger Penrose offers a vision of eternity not as a branching tree, but as a single, endless heartbeat. His conformal cyclic cosmology, or CCC, presents a universe that does not die in a cold, dark whimper, but is reborn from its own ashes in an infinite cycle he calls eons. In this model, our universe's far future, a vast, empty expanse dominated by massless particles and radiation, becomes mathematically identical to the hot, dense soup of a Big Bang. The end smoothly transforms into a new beginning, not through a violent collision, but through a graceful geometric transformation that resets the clock while preserving certain threads of information. The interaction between these successive eons is not across space, but across time, a linear inheritance where one cosmos passes a whisper to its successor. The messengers in this cosmic relay are gravitational waves and massless particles like photons. As an eon approaches its conclusion, all massive particles eventually decay or are swallowed by evaporating black holes via Hawking radiation. What remains is a sea of radiation and ripples in spacetime itself. Penrose proposes that this radiation, and particularly the gravitational waves from cataclysmic events like the mergers of supermassive black holes, can survive the transition. They carry information, a faint fingerprint of the previous universe's structure, directly into the next eon's explosive birth. This information is not lost, it is imprinted onto the newborn cosmos, potentially shaping the large-scale patterns we see today. The most tantalizing evidence for this theory lies in our own cosmic microwave background. Penrose and his collaborators have identified what they call Hawking points, unusual, circular spots of warmer temperature in the ancient light. In CCC, these are not random fluctuations. They are proposed to be the final, fading imprints of supermassive black holes from the previous eon. As those colossal black holes evaporated completely at the end of their universe's life, they released a last burst of Hawking radiation. That burst, stretched and transformed across the eon boundary, would manifest in our universe's first light as a distinct circular warmer patch. Finding and confirming these points is a contentious endeavor, with many cosmologists arguing the patterns are consistent with random chance. Yet if they are real, we are looking at the ghostly signatures of celestial giants that died in a universe before our own, their last breath warming the cradle of our cosmos. This theory provides an elegant, almost poetic solution to one of cosmology's deepest puzzles, the low entropy of the early universe. Entropy, or disorder, always increases. Our universe began in a state of incredibly low entropy, a highly ordered starting point that has been mystifyingly unlikely. CCC offers an answer. The low entropy of our Big Bang was not a beginning but a continuation. The gravitational field from the previous eon, stretched smooth and uniform by its infinite expansion, provided a high-order, low-entropy starting condition for our own. The multiverse interaction here is a direct bequest of order. Our cosmos did not start from scratch, it inherited a clean slate from its predecessor. This paints a picture of multiverse interaction not as a chaotic clash of bubbles, but as a solemn, eternal passing of a baton. Each eon lives, expands and dies, only to have its most enduring essence, its gravitational memory and its light, become the seed for the next. We are not in a disconnected bubble in a foam, we are in the current verse of an endless cosmic poem, each stanza written with the echoes of the one before. The search for proof is a search for our own cosmic ancestry, written in the subtle geometry of the first light we can see, a message from a farther universe we will never see, but whose legacy might be written across our entire sky. Penrose's eternal heartbeat of eons suggests a cosmos that remembers, but what if that memory, and indeed all of reality, is not just stored but actively protected from corruption? The final theory takes us to the absolute frontier, where physics meets computer science in a revelation that redefines existence itself. It proposes that space-time and the entire multiverse operate like a vast, self-healing quantum error-correcting code. In our most advanced quantum computers, information is fragile. A single stray photon or vibration can flip a qubit, corrupting a calculation. To protect this data, scientists use error correction, spreading the information of one logical qubit across many physical ones. This creates redundancy, so if one part is damaged, the original message can be recovered from the intact pieces. The shocking proposal from theorists like Juan Maldaisner and Leonard Susskind is that our universe employs this exact same strategy on a cosmic scale. The smooth, three-dimensional space we inhabit with its clear sense of here and there is not fundamental. It is an illusion, a magnificent hologram projected from a quantum system living on a lower dimensional boundary, like the surface of a sphere enclosing our cosmos. This is the essence of the anti-de Sitter/conformal field theory correspondence, or AD-SCFT, a concrete mathematical blueprint for the holographic principle. In this framework, the gravity and physics happening inside the volume of a universe are perfectly encoded in the entangled quantum states on its boundary. But here is the revolutionary twist that encoding is not a simple translation. It is a quantum error-correcting code. The information that makes up a star, a planet, or you is not stored in one place inside the universe. It is smeared out, distributed non-locally across the entire boundary surface. Your existence here, in this specific location, emerges because the quantum data on the boundary is entangled in a very specific protected pattern. Locality, the rule that objects only interact if they are close together, is not a basic law. It is a side effect of this cosmic error correction. It is the universe's way of ensuring that a local disturbance, a cosmic ray or a stray particle, does not erase you from reality. The system has built-in redundancy, so the information that is you can be recovered even if parts of the boundary are damaged. This perspective transforms our understanding of multiverse interactions. If each universe is a separate quantum error-correcting code running on its own boundary, then contact between them is not a collision of branes or a gravitational tug. It is a glitch, a corruption, or a deliberate crosstalk between these immense computational processes. An error introduced into the quantum code on one universe's boundary could manifest inside that universe as an inexplicable physical event, a particle appearing from nowhere or a law of physics briefly flickering. But if that error is not random, if it carries a pattern, it could be a message. This provides a theoretical mechanism for engineering multiverse contact. A civilization that mastered quantum gravity and holography would not build starships. They would become cosmic programmers. By learning to manipulate the entangled quantum states on their own universe's boundary, they could, in principle, rewrite the physics of their interior reality. They could lower the strength of gravity in a region, create matter from the vacuum, or open a stable wormhole, but they could also attempt to broadcast. By carefully crafting a patterned error into their boundary code, they might be able to induce a correlated glitch in the boundary of a neighboring entangled universe. That glitch would then be projected into that other cosmos as a physical anomaly, a structured event that defies local explanation, a beacon in the language of reality itself. For us, such a signal would be the ultimate puzzle. It might look like a repeating gravitational wave signal with no visible source, or a galaxy that rotates as if it were a perfect geometric solid, obeying mathematical elegance over astrophysical chaos. It would be a signature so clearly artificial, so blatantly coded, that it could only be the work of an intelligence that had learned to speak the universe's source code. This theory offers a staggering conclusion to our journey. The search for the multiverse is not a search for other places, but for other processes in a cosmic computer. The solidity of the world, the distance between stars, the flow of time, all are emergent properties of a deeper, informational reality that is busy protecting itself from noise and decay. We are not just living in a universe, we are living inside a stable, self-correcting thought. And the quiet hum we sense in the depths of physics, the mathematical beauty and the puzzling fine-tuning, might be the background processes of that cosmic computer, diligently ensuring that the simulation or the calculation or the dream continues to run without crashing. The ultimate interaction may not be a journey, but a conversation, waiting to be decoded in the noise between the ones and zeros of existence. We have traveled from the violent shockwaves of colliding cosmic bubbles to the silent whispers of quantum entanglement across branching realities. We have explored universes born inside black holes, mirrored in shadow, and simulated within cosmic computers. Each of these 25 theories, from the holographic principle to the eternal cycles of conformal cosmology, opens a different window. They show us that isolation might be the greatest illusion of all, and that our universe could be just one voice in a grand cosmic conversation. The sheer diversity of these ideas is not a weakness but a testament to human curiosity. We are using the limited tools of mathematics and observation to map the contours of the unimaginable, building ladders of logic to peer over the walls of our own reality. While definitive proof for any single theory remains beyond our current grasp, the pursuit itself is transformative. It forces us to question the very nature of existence, causality, and our place within it. Science becomes more than a collection of facts. It becomes a grand adventure story, with each new equation and telescope observation a potential clue in the ultimate mystery. So, as this journey ends, the real questions begin for you. Which of these visions of the multiverse felt the most compelling, the most hauntingly possible? Was it the intimate connection of quantum branches, the ghostly gravity of a mirror Earth, or the terrifying beauty of a vacuum decay rewriting physics itself? Do you believe humanity will one day hold tangible evidence of another reality, a cosmic fingerprint we cannot explain away? The search continues in labs, in data from ancient light, and in the quiet thoughts of anyone who has ever looked at the night sky and felt a profound sense of wonder. Share your thoughts in the comments below. Let us know which theory reshaped your mind. If this exploration expanded your view of reality, please support the channel with a like and subscribe for more journeys to the edge of understanding. Thank you for wandering alongside us. Until next time, keep looking up and never stop asking what else is out there.